All right, number 7. Below is a graph of h of x, which equals x to the fourth plus x cubed minus 6x squared plus 5. From the graph, we can barely approximate the minimums and maximums and inflection points. So yeah, that appears to be true. Like this minimum, this minimum that's between 1 and 2, I have no idea if it's like 1.5. Well, it doesn't look like it's 1.5. It's some decimal. Then there's one that looks like it's probably at 0, and then one near -2, but it's not exact. So use the equation and the first and second derivative rules to find where h of x has the following. A. Relative extrema. State if each is a maximum or a minimum. List where the graph is increasing and decreasing. So first I'll start by taking the derivative. So h prime of x would be 4x cubed plus 3x squared minus 12x. Okay, and then the thing that I know from looking at the graph, if I'm looking for these minimums and maximums, the slope is 0 at those points. So I'm going to set my derivative equal to 0 and try to solve that. And it looks like it could factor an x out. Okay, and then this is a quadratic, so I might be able to factor that, although I kind of suspect that it would be hard to factor given how these, the values that I'm looking for, they're not exactly -2, and they're not exactly 0, and they're not exactly 1 and a little bit. Although actually, now I know that 0, it is actually exactly 0 because of that x factor. But the other two I think are going to be a little tougher, so I think I'll use the quadratic formula. With a equals 4, b equals 3, and c is -12. So to solve this part in the middle, this little quadratic, I'll use the quadratic formula. So x equals -b over 2 times a plus or minus the square root of b squared, so 3 squared minus 4 times a, which is 4, then times c, which is a -12, all over 2 times a, which we decided already was 8. Okay, and that's going to take a little bit of math, -3 over 8. So, okay, plus or minus, let's see, 9, and then, so there's two negatives here, so I'll just change them both to positive. And then I need a calculator for that. So 4 times 4 is 16 times 12. Let's see, 192 plus 9. Okay, so the square root of 201. So that is kind of a weird number. 201 over 8. And then I will probably leave that as, let's call that -3 plus the square root of 201 over 8. And then the other answer we will have be -3 minus the square root of 201 over 8. So, and I can look at the graph and I already know which one's the minimum and which one's the maximum. But let's see. Okay, so it says, I just want to make sure I follow the directions. Use the equation and the first and second derivative rules to find where h of x has the following. So I think I can say this, but I think I'm following the rules, but I know that the minimum is happening at this negative value, which would happen at -3 minus the square root of 201. So, and divided by 8. And so then I also know that there's another one happening at 0, which I found earlier. My 0 over here. And then there's another one that's happening at a positive place. That would be -3 plus the square root of 201 divided by 8. So that's over there. So I think I can label that. So I've got two minimums. -3 plus square root 201 all over 8. And then another one at -3 minus square root 201 over 8. And then there's maxes, well, just one max, a max at x equals 0. And then looking at the graph, I can say where it's decreasing and increasing. So it's decreasing from -infinity all the way to this point, which I found to be -3 minus the square root of 201 over 8. And then it's also decreasing from 0 to this next minimum, -3 plus the square root of 201 over 8. And then it's increasing at the other places. So that would be -3 minus the square root of 201 over 8 to 0. So this part. And then again from -3 plus the square root of 201 over 8 to infinity. So that is a little bit unattractive, but I think we did it. So for part B, the inflection points. List where the graph is concave up and concave down. So to do concavity, I need another derivative. So that would be 12x squared plus 6x minus 12. And then like before, we know that possible inflection points happen when you set the second derivative equal to 0. So we could solve that. Let's see. That one is a bit tricky. I think I'll start by pulling a 6 out. So I have 2x squared plus an x and then minus 2 equals 0. And then we'll do the quadratic formula again. So I've got A, B, and C. So B is 1. So x equals -b over 2 times A plus or minus the square root of b squared, which is 1, minus 4 times A, which is 2, times C, which is -2, all over 2 times A. Oh, actually, it looks like I didn't write. Ooh, I'm glad I caught that. 2 times A, and in fact, we'll just make this go all the way across because we can. 2 times A is 4. And then since under the square root I have a negative and a negative, I can turn them both to be positives. So x equals -1 plus or minus the square root of, let's see, so 4 times 2 is 8 times another 2 is 16 plus 1 is 17 all over 4. So this is another really wonky number, so I'll just leave it as -1 plus the square root of 17 over 4, and then -1 minus the square root of 17 over 4. And then looking at my graph, I can already see where each thing will be. So there's, let's see, it looks like it's concave down until, concave up, so let's, graph's being copied, concave up till somewhere in here, then concave down until somewhere in here, and then concave up. So I have inflection points. Looks like I have one in here somewhere and one in there. So I know, this is the more negative number. So that's probably that one. And this is a more positive number, which is probably that one. So from that, I can write my intervals. Okay, so concave up. So the first interval is concave up, negative infinity to the more negative number. And then the next one, let's see, and then, yeah, so we skip the middle part, and then, so that would be -1 plus the square root of 17 over 4 to infinity. And then it's concave down in the middle. Concave down from -1 minus the square root of 17 to 4. And over 4, my bad, -1 plus square root of 17 over 4. So the middle part. So that's my final answer there. Part C says, does h of x have a global maximum or a global minimum? So I can look at my graph and answer this. So let's figure out what the answer is, but then backtrack and do it with the equation. So there's, let's clean this up. So there absolutely is a global minimum. And that happens right here. So it's like roughly, I don't know, -12-ish. But there isn't a global maximum because this function continues off the page infinitely forever. So how would we figure that out using just the graph? What I would do is I would test the local mins and maxes. Okay, so we found, let's see, there was a max at 0. So I'll start with a possible max. X equals 0. And so I'd plug that in and into the original equation. And then there was mins, let's see, -3 plus or minus square root 201 over 8. -3 plus or minus the square root of 201 over 8. And my plan is to plug each one into h of x and see what I get. So h of 0, that tells me the actual height. So this one actually should be pretty easy. So if you come up to the original equation and I plug in 0, so this is the original equation. If I plug in 0, 0, 0, 0 plus 5, and that fits with the picture. So the local max for 0 is 5. And then the minimum, that one will be a little tougher. H of -3 plus square root 201 over 8. This one I need a calculator for. At both of them, I'm going to need a calculator for. And it might take me a second because this is a weird one. And as much as possible, so normally I would say you'd want an exact answer, but I just want you to imagine what that exact answer would look like given how big our original equation is. So instead what I'll do is I'll just round to 2 decimals. So -3 minus square root, let's see. Okay, So this is approximately the same as h of 1.77. And then I want to approximate also the positive value. That is approximately the same thing as 1.4. It's 1.4. Okay, and then each one of these I'll put into a calculator. Into this original equation up here. Okay. It turns out I'm using a crappier calculator than I thought. So I'm going to skip this calculator. So what I would do is I would plug in 1.4 into the original equation. And then what's cool is, so now I know that this point is approximately 1.4. Oh, this point right here is approximately 1.4. And when I plug that in, I should get some number that's pretty close to 0. So we're just going to say this is roughly 0. And then 1.77, I would plug 1.77 in. And when I got that, let's see, I should get some number out that's roughly 12. So we'll approximate at negative 12. And that was a negative 2. That's important. Yeah, negative 12. So then what I'll look at is I'll say out of the two minimums, this one is definitely smaller. But then there's this weird thing that happens where you do need to get a general idea of what the function looks like. Otherwise, you might assume that this is your global maximum, but we know it's not the global maximum because the function continues in either direction. So what I would do is I would look to see where it's increasing and decreasing. And I would try to draw myself kind of a picture of what that looks like. So without looking at the picture that I have and using the information that I have here, just where it's increasing and decreasing, I would draw myself a little picture. So I know it's decreasing from negative infinity to a certain point. And then later from 0, it's decreasing again until a certain point. And then the points where it's not decreasing, it's increasing. So it looks sort of like that. And you know, since I'm pretending I don't have a graph, it looks like a W in some way, but I don't know exactly how the W looks. It could be really flat, sort of like that. So you're not sure. You could look at concavity too. So looking at concavity, concave up. So it's concave up to a certain point, -1 minus 17, and then it's concave down in between, and then concave up again. So I'm pretty confident it looks like a W, and I also know that it's decreasing from negative infinity to some point in here, and then it's increasing onward after that. So that tells me there's not going to be any maximum value. A maximum has to be like a solid point. Infinity doesn't count as a maximum. So I would say no max, and then absolute min. So the absolute minimum value is roughly -12. This is kind of a tough problem to get the idea behind, I would not give a problem this difficult, like with such a weird number, except that I think this example makes it kind of easier to see how you would do it. Like it kind of gives you an idea of why you would learn how to do this method and when to do it. I definitely hope this helps. Let me know if you have any questions.